Malthus. He published a book. This is an essay on the principles of population in 1798, stating that population with unlimited natural resources grow very rapidly. Population with unlimited natural resources, they grow rapidly. And according to Malthus model, once population size exceeds available resources, population growth decreases dramatically. And this accelerating pattern of increasing population size is called exponential growth, right? It grows rapidly, meaning that the population is increasing by a fixed percentage each year. So when plotted on a graph showing how the population size increases over time, the result is a J shape. And then this is how it is, right? The exponential growth. All right. When we talk about exponential growth of this, right, we also refer to, when we talk about population of species, right? It's not we only the individuals, with only the human beings. We talk about also, non-human beings like bacteria, some even trees, birds, all of them, they are species. All right. So when we have this exponential growth, it goes like a J like this. So here, population size is on the y-axis, right? Which is the ordinate, and then the time in hours is in abscissa, right? And now, as population is as time goes on, the time increasing, the population also increasing exponentially. That's why we say exponential growth. E to the power of some kind of value, right? We have exponential decay and we have exponential growth. This is exponential growth. It's going up, all right? So exponential growth is seen in bacteria. Bacteria are prokaryotes, organisms whose cells lack a nucleus and membrane-bound organelles that reproduce by fission. Each individual's cell splits into two new cells, right? So bacteria, that's the reason why when they give you medicine, for example, they give you antibiotic, and then the doctor wants you that, you know what, my patient, take this medicine, take them maybe to this time and this time, this time. Please adhere to it, because bacteria, they grow exponential growth. All right. If you don't take them, the bacteria, they will keep growing on and on and on, and then sometimes they even grow resistant to the medicine because you didn't take them at the time that we were supposed to take them. All right. So bacteria, they have the exponential growth. They grow very, very leaps and bounds. All right. So exponential growth model, right? It has this equation, which is G equals to R times N. And we can also express it, in when the limit of it, the time becoming small, you can say dn dt. Right? dn dt, equals to R times N, dn dt. So G or dn dt is the population growth rate. And when you hear the rate, that means there's a time bound. So it's a measure of the number of individuals added per time interval. All right, so we have dn dt equals R times N. The R is the per capita rate of increase. The R is the per capita rate of increase. That's the average contribution of each member in the population to grow population growth. And then per capita means per person, right? Per capita means per capita means per person, right? And then the N is the population size, which is the number of individuals in the population at a particular time. So in this growth model, R is multiplied by the population size, which is N. So population growth rate is largely influenced by the size. All right. The bigger the size, the bigger the growth. The lesser the size, the lesser the growth. So in exponential growth, the population growth rate depends on the population size and the per capita rate of increase, R, right? So in this model, R does not change. That is a fixed percentage, and change in population growth rate is due to change in the population size. All right. So if you have R times N, right? R times N, and R is fixed. R does not change. The rate does not change. All right. If the R does not change, so the growth rate will mostly or largely depend on the N, on the size of the population. So as new individuals are added to the population, each of the new additions contribute to population growth at the same rate. As the individuals already in the population. So the R, right, is equals to the birth rate plus the immigration rate minus the death rate, and then plus immigration rate. What immigration means, you know, I mean, it's very, very simple, explicit. Those who are giving birth come out from birth. We add them to those who are also entered into the society. All right. And then those who have really died, we also add them to those who have left the society. And then we subtract. That will give us the R. So the R is positive. Right? If R is positive, the population is increasing in size, because that means those who are born and those who are also coming are more than those who have died and those who have left. Right? That's how it is. When R is negative, that means those who left and those plus those who um, died are more than the birth rate and those who left the society. Right? So that's how it is. So if R is zero, then the population growth rate is zero, and the population size is unchanging. And when R is zero, so we can say that we can term it as zero population growth, right? Zero population growth. R varies depending on the type of organism. For example, a population of bacteria would have a much higher R than a population of elephants. All right. So depending on the species, the R will be determined. All right. Then we have a logistic growth. Logistic growth. It's exponential growth sizes when the resources become limited. All right. Exponential growth size it ceases. It ceases when resources become limited. We don't get resources, we get food. We don't get food to eat. The bacteria don't get food to eat. Then exponential growth rate becomes it stops. If you get food to eat, that's why you grow and you'll be able to mate and give birth. This is a situation whereby there's no resources. So then the exponential growth rate stops. Then the population exhibits what we call the logistic growth. Logistic growth. In this growth, a population grows nearly exponentially at the first. Because when it just stopped, it will grow a bit exponentially in the beginning because it was growing exponentially, and then there's no logistics, there's no food, there's no resources. then to the exponential growth will go slowly, right? Exponential growth will just when the population is small, right? In this growth rate, population grows nearly exponential at first when the population is small and resources are plentiful. Growth rate slows down as the population size nears limit of the environment, right? Now population is growing and growing, then this no much resources according to how much the population is growing. All right, then resources begin to be in short supply and finally stabilizes. Right. So at the maximum population size that can be supported by the environment, we call it carrying capacity. Carrying capacity. The size of the population that can be supported by the environment. The size of the population that can be supported by the environment. This results in a characteristic S shape. All right. And that time it results in a S-shaped growth. So this is the mathematical function or for the logistic growth model. So it's G equals to R times N times 1 minus N over K, right? The K is the carrying capacity. The N, we know the N population size, and the R is the rate. And G, right, is the growth rate. So carrying capacity is the maximum population size that a particular environment can sustain. Carrying capacity is the maximum population size that a particular environment can sustain. So notice that this model is similar to the exponential growth rate, a growth model, except for the addition of the carrying capacity, right? There's K. This K that makes a big difference. It's almost like, the exponential, just that the K, right, is what makes it a bit different, right? And this is the carrying capacity, all right? It's logistic growth at a hypothetical material population. You have the population size as the number of individuals, and then the time in days, and then we have the carrying capacity up here. So you see the beginning, it seems like it's exponential growth, and then it reaches some point in time whereby the growth rate series, and then it exhibits like S shape, right? Instead of the J, it exhibits the S shape as time goes on. And this is the K, whereby is how much individuals that can be carried by the environment, that the environment can sustain them. That's the carrying capacity. Influence of K on population growth. In the logistic growth model, the exponential growth, that's R times N, is multiplied by the fraction or expression that describes the effect that limiting factors 1 minus N over K have on an increasing population. Initially, when the population is very small compared to the capacity of the environment, right, 1 minus N over K is a large fraction. They nearly equals 1. So population growth rate is close to the exponential growth rate. This model predicts that the population growth rate will be small when the population size is either small or large, and highest when the population is at intermediate level relative to K. So they want it to be, in the intermediate level. So a small population growth rate is limited by the small amount of individuals as a small population. And they are available to reproduce and contribute to a population growth rate. Right? And at large population growth, a large population growth rate is limited by the limited amount of resources available to each of the large number of individuals to enable them to reproduce successfully. So small and big, as two extremes. All right. We don't have many people to reproduce. But when it's big too, the resources are not there to sustain everyone. So then the maximum population growth rate will happen when n is half of k. When n is half of k, then we have a maximum population. So we have some factors that limit growth of population. All right. So in a nature, a population that is introduced to a new environment or is rebounding from a catastrophic decline in numbers may grow exponentially for a while because density is low and resources are not limited. We have enough resources. Eventually, one or more environmental factors will limit its population growth rate. As the population size approaches the carrying capacity and density increases, birth rates may decrease due to limited food as population growth, and death rate increase due to rapid spread of diseases as individuals encounter one another more often. So you see, sometimes when the population grows to a certain number, it's not good. And when it's low too, it's not good. So then we need intermediate, some form of intermediate. Because when it goes higher too, it's a problem. I remember, those COVID time, those also in the cities too, they were affected most. Uh, I learned that in New York, like this, New York, when you enter the train, right, during the rush hour, there's a whole lot of, people, they be as if they have been stepping on one another, whole lot of people in the train. And then the COVID affected them a lot, all because, people will hold and, if you don't get a seat, you hold on the bar to stand in the train. And other people will also be standing, hold the bar. Maybe you touch your nose and then, or you touch your mouth. So, and then you use it to hold the bar. Somebody also come and hold the bar. If you have the COVID, that somebody also have the COVID when he holds the same place and then touches his mouth or nose. So New Yorkers died a lot. They died a lot. So when the population is big, very big, sometimes it becomes a problem. And when it's very small, it becomes a problem. So we need in the middle. So the impact on birth and death rate in turn influences the per capita, per person rate of increase and how the population size changes with changes in the environment. When birth and death rates of a population change as the density of the population changes, the rates are said to be density dependent, and the environment factors that affect birth and death rates are known as density dependent factors. All right. So if there's a problem with the environment, right, and then the density of the population change, right? The density of population, we say it's a density dependent population, right? The environment too, can affect birth and death rates, and we say density dependent factors that affect them, say density dependent factors. Factors that are not related to the density of the population are called density independent factors, right? And influence population size regardless of population density. All right. Any questions so far before we move? If you have any contribution, you can also add, or if you have any question. Kingsley, is Kingsley there?
Yes, sir. Please, I'm here.
Oh, Kingsley, today you are here. That's good.
Yes.
What
Sir, I
about
used to be here.
what about engineer Philip? Engineer Philip. Philip, Engineer Philip, are you there?
Sir, he said He's on the way. He's way to work, so he'll be joining late.
So you, Kingsley, you and Philip are going on a shift. When you come, Philip does not come. If you
Oh
Philip
no,
comes, you don't come. You're on a shift. Huh?
no
Kingsley,
sir. Sir.
you're an engineer. You're on a shift. I've known it.
Oh no sir, no sir.
Are you sure?
Yes sir.
The last time you were not here, Philip was here, and then today you are here. Philip is not here, so you are going on a shift. Anyway,
Yes, sir, it's a coincidence.
are you sure? Yeah, I'm telling you guys.
Yes sir.
Okay, so factors limiting population growth, right? Most density dependent factors are biological. Most density dependent factors, they are biological in nature. When we say biological in nature, we say biotic, and they include certain things like predation, right? Predation, or and the inter and intra specific competition for food and bait, accumulation of waste, diseases such as those caused by parasites, right? And let's talk about the predation. Predation, some individuals, species eating others, killing others. They predate on them. If you go to a population whereby these tigers are there, and then they have goats there, they will not spare the goats. Okay, so they'll try to eat all the goats, and so the population growth rate will go low. Same thing, lizards and insects, predation. Lizards can also eat more insects and stuff like that. All right. So when individual species are also, eating others one people or killing them, uh, then we have inter and intra-specific competition for food and mates. Right, for food, right? They are all fighting for the same food. Sometimes we human beings we also do the same thing, and we also fight. We and then some animals. You grow your food, and then you come and sleep. By the time you go back, some animals also have eaten your food. The one that you grow, they come and destroy it and eat it. It happens to the farmers a lot. You get it. So we also compete for those kind of food. And the individuals too, the same food too. Some individuals who can be fighting for the same type of food. Now Ghana is good. That some years ago, that Ghana we were fighting for food. And so now food is abundance in Ghana during 1980s, 83, 82. There's food shortage in Ghana. There's more like the fire outbreak all over the place, and we didn't have food. And when people are, the bakers, those who bake bread, they are baking it, people will be queuing to wait when the bread is baked, then they will buy it. People were fighting when people mowed the kinky. People will go and buy it from those kinky sellers and go and cook it themselves at home. It wasn't easy. That's why we have something we call the Rawlings chain. Individual grew so lean. We're fighting for food. You understand? And it affects people were dying. The older people were dying, children were dying, all because there was no food. All right. Might say accumulation of waste. Right. Let me go back to the mates thing. And people fight for mates. You know, I said it before. If there's not much, like for example, not much male and not much female, and then female are more, and then male are less. You see, people will not get made to meet um, partners to really give birth. All right. Same with the animals. Same with the animals. All right. And same with other species too. And accumulation of waste too. Accumulation of waste. If there's so much waste, all right, in a society, people can get sick. People can get sick and then die of. And also diseases such as those caused by parasites can also make people die. It affects the population growth, right? The population growth. Usually, higher population density results in higher death rates and lower birth rates. All right. Usually, higher population density results in higher death rates and lower birth rates. Okay. Example, as the population increases inside, food becomes scarcer. Right? Some individuals will die from starvation, meaning that the death rate from starvation increases as population size increases. Yeah. So as the population size is increasing, we need to now technology is helping. But when we talk about species like animals, other species, for them they don't have the technology like we the human have it. That makes sense. So it becomes a problem. So they will die. As food becomes scarcer, birth rates decrease due to fewer available resources for the mother. All right, so food is getting scarce, and then the mothers will not get enough food because the younger ones, right, they depend mostly on their parents, their mother. And if the mother does not have enough food to eat, even their breast cannot give more milk, and then the younger ones will die off. All right. So the birth rate decreases as population size increases. For density dependent factors, there is a feedback loop between population density and then the density dependent factors. All right. So this is a factors limiting population growth. And we have this average clutch size, the insect, and the number of breeding pairs. All right. So the clutch graph of clutch size, number of eggs per liter of the great titbit birth as a function of population size as a breeding pairs. Clutch size decreases as population density increases. Why? Because you see, there's the food that are available. All right, they cannot really sustain them that well, so they become smaller, smaller, and then some of them dies off. So the average crop size is increasing, and then when the population, the number of breeding pairs decreasing. All right, so this is a negative curve. All right, density independent birth rates and death rates do not depend on population size. Density independent birth rates and death rates for them they don't depend on the population size. These factors are independent of or not influenced by population density. Many factors influence population size regardless of the population density. All right. Many factors influence population size regardless of the population density. Whether the population is big, whether population is small, whether population is intermediate, are some factors that affect the population. It doesn't matter the size of the population, something like weather extremes, right? Population does, I mean, weather does not care whether individuals are plenty in Ghana or they are small in Ghana or in your village or my village. You understand? When it's cold, especially when I go to cold and that place is cold, it doesn't matter whether I'm the only person in my hometown or we all the cold people are there. It doesn't matter. All right. So the natural disasters. When there's natural disaster, something like an earthquake, it doesn't care whether it's only one person in that city or village or wherever it is. This one it doesn't care. That's one of the factors that influence populations are regardless of the population density. It will affect it. When there's an earthquake, people will die. It shakes the earth. Sometimes opens it, and then there's lava. And then destroys houses and this. Like also hurricanes. When hurricanes that happens, it affects people. That doesn't matter whether there's only two people in that around that place or not. Tornadoes, tsunamis, and so forth and so forth. Those natural disasters, they don't care whether we have only two people at that vicinity or we have the whole world population under this, vicinity. They don't care. Pollution and other physical factors. Those are the abiotic factors. They don't care when there's pollution in the air, right? And something like maybe carbon monoxide is in the air. It doesn't really care whether really plenty people are in that environment or not. You know, at dawn, for example, you are around, and then these cars that emit a whole lot of pollution in our environment. They are moving and they go to town, and there's a few people there. They just emit their pollution. They don't give a damn about how many people are there. But same much the same way during the daytime when plenty people go to Kaneshi and Circle and all those places, and a whole lot of people are there. The population, the pollution will be just with pollution, polluting the air. So those ones, they affect the population side without, they don't care about the density of the population, all right? They will just come and affect it. Right. Factors limiting growth rate again. For example, an individual deer may be killed in a forest fire, regardless of how many deer happen to be in the forest. All right, whether it's two deers or four deers or 1,000 of them, they don't give a damn. They don't care how many deers are in the forest. Right? The fire will just go in there. Doesn't care about how many fires there. The forest fires is not responding to the deer population. No, populations are not. In other areas, as the weather grows cooler in the winter, many insects die from the cold. All right. For example, in Ghana, our weather is not too cold here though, but sometimes it becomes very, very, very hot, right? And when you go to a place where it's cold like this, mosquitoes, they don't like cold weather. Yes, they don't like cold environment. So they die off, right? Change in weather does not depend on whether there's a population size of 100 mosquitoes or 100,000 mosquitoes. Most mosquitoes will die from the cold, regardless of population size and weather, and the weather will change irrespective of population or mosquito population, all right? So if you switch on your AC in your room, and the population that are there, the population of mosquitoes that are there, if the weather two mosquitoes are or 100 mosquitoes, they will die off. So that's how there are some factors that limit the population growth, regardless of the population density. All right. So this is number of aphids, and this is the month. Weather change acting as a density independent factor, limiting aphid population, aphid growth. This insect undergoes exponential growth in the early spring and they rapidly die off when the weather turns hot and dry in the summer. So this insect, when they grow high, exponential growth, and then when the weather favors them, and then when the weather disfavors them, then they go down, die off. All right, they die off. In a real life situation, density dependent and independent factors interact. Right? They are not extreme in real life. For example, a devastating earthquake occurred in Haiti in 2010, the year 2010. Earthquake occurred in Haiti. Haiti is one of those South American um, countries. When you in the US, they are there a lot, and I used to encounter them. And these people, right, when they speak like the Ewe, when they are speaking, they have Creole. One of their languages is called Creole. And this Creole, when they are speaking, you may think they are speaking like Beninois, Beninois language. They do themselves like they're Beninois. And then the Togolese. They are very interesting people. And the Haitians, the earthquake that happened in Haiti, right? And then and when they were there, right? This earthquake is a natural in a disaster. All right, when they were there too, they would put them in a refugee camp because the earthquake had destroyed their habitat where they live, these people live, and now they say let's put them in a refugee camp, and then the refugee camp too. Then there's a spread of disease. All right, there's a spread of disease because people were not sanitary enough. They didn't keep themselves clean, so then the disease spread up. But few people living at a camp like that, the speed spread up. So this is the density dependent because the people were that many at a few places. The density was big. Population density was big. So and the diseases spread out quick, 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 all because there were many there. So and this is a situation whereby density dependent and density independent things occur. The independent one is the one that the earthquake that happened, and now the dependent one is also when the disease also spread out because there were plenty people living at a smaller area. All right, so that's how it is. All right. So now, if you have any question or contribution, you can bring it out. Otherwise, we move into different thing. I'm waiting. Right, nobody has anything to ask or offer. So let me move on with my talking. All right. We have this called live tables and survivorship. Live tables and survivorship. Uh, who can tell us what live table and survivorship is? Have you encountered live table and survivorship before?
No, sir.
Kingsley. Oh, okay. Nobody has done that before. All right. So now
No, sir.
I'm going to be
Okay,
looking at
no.
your name and then also be asking you questions. Yes. Yeah, I have to ask you questions. All right. Okay, let's go. We move on. Population ecologists. They use live table to study species and identify the most vulnerable stages of organisms. Right. The organisms like to develop effective measures for maintaining viable populations. All right. So it's a table, right? Population ecology. They study how individual species they can survive at different stages in their lives. All right. Whether they can survive when they were young, and then when they grow to a certain level, they die, or when they die when they were young, and then the younger ones when they are able to survive to a certain age, then they can grow very old. So that's how population ecologists they do, and also when they do that, then they see that okay, then let's help these individuals to be able to really live at a certain point in time or a certain point of their age. And so that's what we are talking about here. Right? So life tables, right? Life tables track survivorship. Life tables, they track survivorship. The chance of an individual in a given population surviving to various ages. So life tables were invented by the insurance industry to predict how long on average a person will live. All right. Who has done insurance before? Who has insurance?
Yes, sir. Sir, I have insurance.
Oh, okay, that's good. That's good. You're a smart guy. Insurance is good. Insurance, uh, we have life insurance, right? And then we have this automobile insurance and your properties, your houses and other stuff you can insure them. In case of eventuality, then you can really get something from it. But for life one, most people don't want to do that. Can you tell me the reason why they don't want to do that? I don't know.
Sir, for me, my reason was Once I am alive, I don't have to die before someone will come and enjoy my money. I don't have to ensure my life. Then something will happen to me, I'll die. Then they say my nurse of kin or my family members will claim that amount of money to spend. So for me personally, that is why me I don't entertain certain things.
Uh,
Even the insurance that I've done, sef, I want to cancel some. I did an
uh,
insurance for my small boy, and per
uh,
my calculations, I'm thinking the insurance I should rather turn it to investment. So once they are deducting every month, I will turn it to investment. Then it will be investing. Like the investment, this thing every month they will deduct automatically, like the insurance.
mm,
I'm thinking of the two, so I'm making the inquiries whether the investment will be better than the insurance.
uh, I see. But then, I think for individuals there, when you make insurance, you can put your beneficiaries to be your children. Since you love your children, you can put it, make your children the beneficiaries so that when you die, it's not your family members who will come and take your money. But you didn't somebody give birth to you. When you were young, didn't your family members help you? So if they take your money when you die, what's wrong?
They will intentionally kill you and take you to your grave early if they find out.
But maybe when you are alive, you were not, really giving them some of your money. So that you chopping the money, you leave them. So why would they, get rid of you so that what you have for them, they will take.
But
Oh,
but honestly, before I was doing the insurance, oh, but in Ghana, yeah, when you're making claims, it's very difficult.
oh, okay. Uh-huh. Uh-huh. If you are making claim
When
here
you're
in
making
Ghana,
claims, it's very difficult. Yes,
oh, I see.
it's very difficult.
Oh, I
Yes,
see.
but aside that, oh, I
Mm,
see no problem with the insurance. But there are some companies, if you are not well, like educated about them, making claims is
mm.
very difficult. Even your next of kin, you'll find it difficult to make a claim.
Oh, I see. I see. But outside it's not like that. I remember my elder brother. He passed away in Canada. He made insurance of about $250,000 for his children. And then when he passed away, they gave the money to the children. They didn't have to hustle. Once they showed that this in the birth certificate, I mean the death certificate, legitimately they gave him the money. I don't know why Ghana in Africa we always try to cheat one another. I see no reason why. Ghana, even sometimes when you work, there's some people go to work and the people don't want to pay them. And somebody has worked for you the whole month and you don't want to pay them. So that I agree with you on that issue. Now, other than that, I think insurance is good. For me, when I was a student, I worked for an insurance company. Before, I worked for John Hancock. We have different type of insurance. Some of them too, you don't have to die for somebody to really come and enjoy your money. Sometimes we have this insurance that we call whole life insurance that you can even claim part of your insurance and then chop it whilst you are alive. Yeah, and chop your own money. So insurance is good. But these life tables were invented by insurance industry, right? For them, they are smart. They did that to see, okay, if we can say that these people at this age they can die, so they will increase your premium, all right, the money that you will pay to them before. Because if you are young, they say that okay, when you are young, your chance of surviving will be long. So you pay more money, you pay more premium before you die. But then if you are old to a certain age, okay, and you live in a certain area, you come from your background and this and that. No, this guy, this lady, she will die early. So then your premium will go high. So that's how they do. So it was invented by the insurance industry to predict how long on an average a person will live. Right? Biologists use a life table as a quick window into the lives of the individuals of a population, showing how long they are likely to live, when they will reproduce, and how many offspring they will produce. And this thing too helps. Beside these insurance guys, they also help us to also predict how long we can live. And when we are making infrastructure, our roads and this, we can say, okay, our population can grow to a certain level, people will be living, so then we can make good in, open up our infrastructure for people because they can live longer. And also our hospitals, we can say that we can get many old people who are at this age, and we can do that. So it will help us to make predictions, those life tables, all right? Life tables are used to construct survivorship curves. They are graphs showing the proportion of individuals of a particular age that are now alive in a population. Survivorship, that is the chances of surviving to a particular age, is plotted on the y-axis as a function of age or time on the x-axis. Mostly the ones that are independent, right? When we are making plotting, the ones that are independent, we plot them on the x-axis or the abscissa or x-axis. And then the one that is dependent, you plot it on the y-axis, which is the ordinate, right? Axis, right? So if the percentage of maximum lifespan is used on the x-axis instead of actual ages, it is possible to compare survivorship curves for different types of organisms. All right. And time is independent factor. So that's why most of the time when you are plotting, we plot it, the time on the x-axis because time is always independent. As we are sitting, we are learning now, whether we learn or we don't learn, time is moving, so it becomes independent, right? Independent. All survivorship curves start along the y-axis. The y-axis intersects with all of the individuals in the population, or 100% of the individuals survive. As the population ages, individuals die and curves go down. The survivorship curve never goes up. Survivorship curve never goes up. It always goes down. Right. So here this is a table, right? A table of survivorship. Where we have the age and we have the number of living at the start of the age interval, and then we have the number of dying during that age during the interval, and chance of surviving interval, and a chance of dying individual interval. So this table you can construct it yourself. See, it's from 0 to 1, right? Let me go back. 0 to 1, right? We have 100,000. It was adapted from the US. Now I try to get the survivorship table, right, from Ghana, but it wasn't helping me, so I used the US. All right, I use the one for the US. So it's from 0 to 1. There are 100,000 people. All right, 100,000 people. And the number of dying during this interval was 606. All right, the chance of surviving interval was 0.9934942. A chance of dying is during interval is 0.006058. You see, the chance of dying is very low, all right, very low compared with the chance of surviving, 0.999. I want you, when you have the notes, I want you to find out how these numbers came up. Now, this one, 100,000 is there, right? And 606, you know, is there. All right. So how did they get the chance of surviving and then the chances of dying? Those numbers, these two numbers. Try to find out. And when you're coming down to, they go down on and on and on and on. So this one is retrieved from here, and this one is retrieved from here. So you can find out going down and down and down. So now, just in case you become, a national statistician, or something, somebody like that, you can really bring this out, survivorship table, and then you can, show them how to construct it, and then it can help you. All right. You are electrical engineer, but life can change. You may do something else because you know it, you are learning it. So you can do something else besides being an electrical engineer. You be an electrical engineer doing something in relation to what you have learned. This is part of your course. Okay, so that's why I want you to find out how this table came about. All right. So for the top one, right, the top one is there all the way here. It is there up to this time. And the rest of them are derived from this side here. All right, the rest of all of these are derived from this side here. Sorry. All right, these ones, they come from the top. All right. That's how it goes. All right. So you just have to learn how to do it. All right. So survivorship curve reveal a huge amount of information about the population. Right. Survivorship curves. It tells a lot about population. It tells whether most offspring will die shortly after birth or whether most will survive to adulthood and likely to live long lives. All right. So those curves, go to the net, look for survivorship curve for Ghana. All right. You see them, they are there. But like I said, the explanation on it is not really, really great. So that's why I use American stuff. So we have these three types. Right? Organisms generally fall into one of three types, uh, three typical shapes, type 1, type 2, and type 3. Right? Those are survivorships. So organisms that exhibit type 1 survivorship curve have the highest probability of survival every age interval until old, and when they get old. So the risk of dying increases dramatically when they get old. When they get old. Humans are an example of species with a type 1. We human beings, right? Human beings, we are type 1. Because every age we have a chance of surviving. Right? Human beings are an example of it. Others include giant tortoise and most large mammals such as elephants. For them too, they are like we human beings. They can survive at every age. These organisms have fewer natural predators and are therefore likely to live long. Now, all right, we human beings, we predate on other uh, animals or other living organisms because God has given us more wisdom and understanding and knowledge. And we say knowledge comes from learning. All right, so we are learn and we learn these things that we can use to defend ourselves. All right, we have houses, we build, things that scientifically we have scientific things that can help us. All right. So these organisms have fewer natural predators and therefore likely to live long life. Elephants like this. If you're a tiger, you go and attack elephant, you run. There's some animals, tigers don't attack them when I'm watching the wildlife, because they won't survive. All right, because they also defend, they protect their young ones. All right. Reproduce only a few offspring at a time, and invest significant time and effort in each offspring, which increases survival. We human beings like this, all right, the type 1, we has be type 1, right? We invest more time when the baby comes, the way we cuddle the baby, we protect the baby, we give them, good things. We even um, boil their babes, and we boil the one that we give it the feeding bottles. We clean them. We invest more time to make sure that they will survive, those that they don't catch any diseases. And every age we try to make sure that we don't die early. And so we don't give plenty. Just a few situations. That one is anomaly. That individual will give birth to 3, 2, 4, and so forth and so forth. By majority of the cases, you know, vast majority of the time, we just give birth to one individual and we invest more effort, we spend more money to make sure the individual survive. All right. Then we go to type 3, type 3 survivorship care. Most of the deaths occur in the youngest age, right? Type 3. Yeah, juvenile survivorship is very low, and many individuals die young. The individuals lucky enough to survive the first few age intervals are likely to live a much longer, right? most plant species, insects, frogs, as well as marine species, such as oysters and fishes, have a type 3 survival. It's true. Because you see, I have some water. I'm trying to create a water fountain at my house. You understand? And then I have this water there. I pour water, and then they were doing the building for me. And then I fetch water in it. And then some short time, I saw that frogs have entered that water fountain. It was just like water tank that I made for them. Before I would use it for the water fountain, I made it a tank. And this frog, they gave birth. They lay eggs. And come and see how many eggs are in the water. Plenty. They lay the eggs like as if it's a line. Plenty of them. Within a short time, they have plenty of that. I can't even count them. You understand? So there is big type 3. And then most of them are going to be dying because we start fetching the water, throw them away, using to do different things. So that's it. And those like fishes like this. For example, if you can make a fish pond and then you can really breed a fish. Those who do that, they make plenty money. Myself, I'm planning to make fish farm though, so that I can make money out of it. And if I'm able to take care of this fish, because they breed a lot, millions of eggs, and if they can lay plenty eggs, and I'm able to take care of this fish, look at how much money. And if they can, I can get about 500,000 or maybe 1 million fish, and I'm selling one fish for maybe 10 cities. See, I become a millionaire in a short while. So I'm planning. Honestly, and maybe I'll have to stop lecturing and go and do fish farming.
Uh, Sir, please let me ask, what type of fish do you want to invest in?
Now I'm making research. I haven't really found a fish that some people fish, they farm tilapia. Some of them farm this thing, different type of fishes. So yeah, I'm thinking. Just a second. Just a second. Somebody's calling. Kwachi. Kwachi. Mami, 1 minute. Make sure I kakra me bi a member fie na yaba me ho wa ya yaka adwuma no. Why? Kwachi. Yes. Yes. So no, I don't know the type of fish that I want to know the kind of fish that I can make plenty money. Yeah, I won't be talking again for somebody to pay me. I'll be doing my own business. As a Kwama, we like to do business also. I don't know which kind of fish do you recommend?
Catfish.
Okay, because for me, I am doing catfish and I have about thousand catfish.
Hey, then you need to come and help
Hey.
No, I'm telling
Honestly,
you,
Sadat, go and help. Go and help.
I'm serious.
yeah, I have about 1,000 catfish in my house. I am doing catfish
Hey,
at the poultry.
hey, you don't mean it.
Massa, you have
Sir,
money.
I
You have
can send
money.
you. I'll send you videos. I'll send you
Sada,
videos.
Me too. Send us
Sada,
videos. Send us
send me
videos
video,
to
send me
boost
video.
us.
Okay,
Sadat,
sir.
I want to start point and kill.
Hey,
No
Sada,
problem.
send me video. See, you need to make money,
Yes.
See, fish like this, they breed plenty. So if you're able to take good care of them
They breed.
and they don't
Yeah,
die, you'll be rich quick. Come on, you'll be rich quick. You don't have somebody doesn't have to employ
because
you to make
the
money.
catfishes,
Sada, talk.
catfish like this, they don't die. They don't die like the tilapia. The tilapia, you need to have, I think, a running water, like those are the dam,
Um,
the density area. But
um,
catfish is very strong. No matter how, yeah, the weather is or the water looks, they will survive.
they will survive. I see. Sada,
Yeah,
we have to talk
they will
after here.
survive. Yeah, they are very strong.
Let's talk after here. I'm telling
Yes,
you.
sir. Yes, sir.
Yes. You see
Yes,
that I'm
sir.
also learning. You see that I'm also learning something from you. Eh? Where's Yara? Yara is there. Yara is not there. Okay, no problem. All
She's
right,
cooking
so
for the
so so mean survivorship, right? The type 3 for them, they breed plenty. They breed plenty, but then they their young can survive. All right. And but a few of them can survive. The few of them that can survive, they can stay for longer before they die. All right. So that's type 3. The young does not survive that much, but then the few that will survive can live longer. Right. Then we come to type 2. All right. The type 2. The type 2. All right. So the next one, they're talking about mackerel 2. Mackerel 2, they can lay plenty million eggs. Right? Female mackerel, they can lay millions of eggs. Wow. And on average, only two survive to adult. Oh, millions of eggs. Oh. So if you can get millions of eggs and then only two survive, if you can keep them and they don't die, you make plenty money. So organisms with this type of survivorship tend to produce very, very large number of offspring because most will not survive. They also tend to provide much parental care, if any. They tend not to produce parental care, if any. All right. Right then, type 2. Right, we talk about type 1, like with the human beings. Type 3, like the fishes and then the frogs. And then type 2, is the intermediate between the others. And suggests that such species have an even chance of dying at any age. For them, they have even chance of dying at any age. Many birds, small mammals such as squirrels and small reptiles like the lizards have a type 2 survivorship curve. The straight line indicates that the proportion alive in each age interval drops at a steady, regular pace. All right, I'll show you the graph of them. All right. The likelihood of dying in any age interval is the same for the type 2. All right. In reality, most species don't have survivorship curves that are definitely type 1, type 2, or type 3. They may be somewhere in between, somewhere, but they fall more onto 1 or 2 or 3 type. All right. These three, though, represent the stream and help us to make predictions about reproductive rates and a parental investment without extensive observation of individual behavior. All right. For example, humans in less industrialized countries tend to have higher mortality rates in all age intervals, particularly in the earliest intervals when compared to individuals in industrialized countries. And it's true. In the other industrialized nations, for example, in Americas, the individuals, the kids, they give them, when you give birth to your child, you can go in for, vegetables, fruits, milk, food. All right. They give you food for your children. You can go there, your babies, they take good care of them. That's some even countries, when you give birth to the child, they pay them. All right. For me, I lived in America, and then my son, when my wife gave birth to my son, she used to go for food for ensure milk, go for vegetables, go for this, go for that, so that the individuals and the kid can really live well. Now he has his own baby under the crib nicely. He has his room and this and that. That's some places, individual, babies, they won't even allow the baby to live with the same room with the adults that have the same room. Nice places. Also, industrialized nations. Now, Ghana too, we are not that bad, to be honest. We also take very good care of our babies. Right? But at some places, they don't have that much resources. Unlike, we that we do have it. We talk about our country. Our country is not that bad if you compare with some other nations. Those who have traveled to different nations, they know our Ghana is not that bad. But we want it to be better for us so that we can be like, those industrialized nations, right? So looking at the population of the United States in 1900s, you can see that mortality was much higher in the earlier intervals and throughout. And then throughout, the population seemed to exhibit a type 2 survivorship curve, similar to what might be seen in less industrialized countries or among the poorest populations. All right. So these are the survivorship curves of the individuals. We have type 1, type 2, and type 3. Human beings exhibit type 1. Some birds and some other species exhibit type 2. And then trees, frogs, some kind of, fishes, type of fishes, they also exhibit type 3. Type 3. So these are the United States that population survivorship curve that I was talking about. But in 1900s is there. This is the 1900s survivorship curve. 1950, 2000, and then they projected to 2100, 2050. So they did that projection to say that, okay, in 2050, 2100, people will not die, few people will die. So that's how they did. We finished for today. God willing, tomorrow we'll meet in the morning. What time are we meeting tomorrow morning? Kingsley, what time are we meeting tomorrow? I believe it's 11:30.
Yes, sir. 11:30. 11:30.
11:30, right?
Yes, sir. That's
Okay,
chemistry.
Yeah.
So 11:30 to 1:30.
Oh, 11:30 to 1:30. Okay. All right. So, gentlemen, today we don't have ladies, so I won't say ladies and gentlemen. Ladies and gentlemen. I'll say gentlemen. Kiara didn't show up today. I don't know why. Somebody says she's cooking. But now the women, they don't cook like years before. Now the women, some of them, the men cook for them. If you, I don't know if some of you have gone out to live in America or UK or outside, you're meant to come home. You come home, you cook. If you don't come home, you don't cook, you're in trouble. The Ghana men there, you are lucky. You come home, your wife has already cooked for you. For outside, the woman is really bringing money, plenty money. Sometimes the women even make more money than you, the man. So you come home, you cook. Sadat.
Yes, sir.
Do you cook? Do you know how to cook?
I know how to cook, but honestly, I don't cook any longer because my wife does them.
Your wife does it. Oh, you're lucky. But Bernard is not. Bernard. Kingsley, are you married?
No, sir.
Oh, so you cook by yourself?
Yes, sir.
Oh, okay.
I married before, but I couldn't stand the pressure, so I decided to cook.
Kingsley. Marriage is always the same. Marriage is the same, Whether you're married 1,000 times or 10,000 times, it's going to be the same, And marriage, mommy about.
But sir, a BDA, no, I don't know. But
Animal
Ebi
a
did be actually. Ebi did be actually.
BD, I stopped doing too much.
Ebi there. And you better so. Anyway, young friend, could be in idea. Tomorrow, God will meet. Okay. Have a good evening. Yeah. Have a good evening. Yeah. So that we'll talk. We'll talk about the fish.
So he has to take us through education on the fish. So at least if it is 100 pieces that we can, then we'll be doing that in the house, small.
Yes.
Exactly.
Yes.
Exactly. So that you
I
have
think
to
Now
look
they
at
are
it.
that
using
one
this
is okay.
white poly tank for them. So your normal water in your house and other things. So I don't know the amount of fishmongers that a white polythene tank can contain. But some people are
Uh,
using it in their house. Small, 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 small.
uh,
So you have to
oh,
take us through education and
we
before
need education because we all need money. Me, I want to be a multi-millionaire, so you know,
that is it.
I think maybe this will be my breakthrough anyway. Because I've been thinking about it for long. Anyway, so we'll talk. We'll talk, guys. I will see. We see you tomorrow, God willing. Yeah,
Okay, sir. Thank you
sure.
very much, sir.
You're welcome.
Your class is always interesting.
Thank you.
You always come down to our level.
Oh, thank you. Have a good night.
Good night.
Mhm.
Now the day is over.
Hey, Masha. Oh, but Charlie, I will send some video to the page. Then they can
Okay.
do some estate uh, conference meeting, international estate developers conference meeting for Ghana. But how I'm seeing
Okay.
the thing, it means for some time to cannot start from now onwards. Raising of higher buildings and apartment and estate and
Yes, that long building. They will start building
so
some in Ghana
we have to
for apartment.
we those into the business. Let's update ourselves to suit that kind of level this thing.
Yeah.
Because such buildings are coming into
Yes.
the
You
country.
have to make that mind go that point. You need
Yes.
money.
Well, investors are coming into the country for this
Yes.
estate. So I'll be sending the video to the
Okay,
page
but Chris,
for you.
we will talk. We will talk on something too. Don't worry.
Okay. All right. All right. Good night. Good night, everyone.